have Cyril Closset, and he will read between the lines, the sections of Seiberg Witten. Not between the lines.
Really set them up.
Thank you to the organizers for this nice conference and for inviting me to talk. So yes, today I would like to read between sections. I will tell you what that means. The first third or half of the talk will be, well, third, let's say, will be just pure mathematics, very elementary stuff, just so we're all on the same page. And then we'll go to some physics. Now, what's the context? The context is 4D and equal to supersymmetric field theories, and I will be on the Coulomb branch, which we learned this morning is boring, but you know, it's still cool for some of the things I want to do. Indeed, the carving is boring, but there are other things you can say about the Coulomb branch. Yeah, so my apologies, it won't be symplectic singularities in this talk, but we'll leave that as a challenge in the outlook, or to connect to more to the symplectic singularity context, which will be, let's say, 3D Coulomb branch. But today it will be about 4D Coulomb branches. All right. So, as I said, context is 4D and equal to supersymmetric QFT. And we will look at the Coulomb branch. So on the Coulomb branch, that are denoted by B, curly B, and I will take it of rank 1, which means that the Coulomb branch is really one-dimensional. So it's one copy of C. Although for physical purpose, it's useful to keep the point at infinity because a lot of physics happens there. So we'll just add the point at infinity there. So really the Coulomb branch is some pi 1 where you just fix the point at infinity. This is where like you have a semi-classical physics happening, some classical cusp. Then from Seiberg Witten, some obscure paper from '94, just kidding, 2 papers, relatively well known. They tell us that the low energy physics is given by this picture, meaning you have a Coulomb branch. This is my modular space, one-dimensional here by assumption, and you assign to every point on the modular space an elliptic curve, an auxiliary construct that helps us reconstruct all the low energy data of the physics. So mathematically, what we're interested in are a one-parameter family of elliptic curve. This picture, so one-parameter family, so it's fiber everywhere almost, except the curve could have some degeneration over some point, which are well understood. The typical degeneration we'll see today are just double points like this. So this is the standard elliptic curve, written here as a torus, and it could pinch like this with a double point. That's one possible degeneration of an elliptic vibration. I will work exclusively with the Weierstrass model. So an elliptic curve in particular is a cubic that you could write a cubic in P2. We just write on an affine patch. So in terms of 2 coordinates y, x and y. So the Weierstrass model for the elliptic curve. So any elliptic curve can be written in that. By change of coordinates, y squared equal 4x cubed minus g2 times x minus g3. And g2 and g3 are rational functions on pi 1 on my base here. So yeah, so like this, g2, g3 are elements of the field of function on pi 1. So given a smooth elliptic curve, written like this. There is an isomorphism to the standard torus on so to C mod to C divided by lattice, so that my standard torus like this, when I have lattice elements, we call omega A and omega D, some two complex numbers. So L is this lattice. Omega D is Z omega A. And of course, with the modular parameter, which is the ratio of those two numbers called the period. So, right? So, in terms of the elliptic curve written like this, omega A and omega dual are indeed the period over some basis of 1 cycles of the unique holomorphic one form on the elliptic curve. Or integrate over 2 1 cycles on basis of A and B cycle. And well, the explicit map here, just for completeness, if you have a point in C mod gamma, then you map to xy equal p z p prime of z. Curly p, it's hard to write curly on the board, is a standard Weierstrass function. So it's defined in terms of the periods. Okay. For later purpose, it's also useful to note that there is a simple isomorphism between curves that will be useful. I could always rescale, so that those will be the so-called homotety, I guess. So that just means rescaling, where I just rescale the periods, omega A, omega D, rescaled by a common factor, alpha. Where alpha is a non-zero number. This is the same as rescaling G2 and G3 by alpha minus 4 G2 and alpha minus 6 G3. Right, so this is just rescaling by a factor alpha when it doesn't change tau. It's isomorphic elliptic curve. Will be useful later. Let me call that alpha. That's just an operation on the elliptic curve. So that was point 1.1, I guess. And the second point is I want to discuss briefly sections and isogenies. Okay, so given an elliptic curve, let me call it E. Well, the standard thing you do when you first learn about elliptic curve is first considering it over Q, for instance. That would mean that G2 and G3, instead of being function of U here, are just rational numbers. Then we can look at the rational point, typically equal this. So those are the solution to the Weierstrass equation that I erased. So let me write it like this. Again, 4x squared minus G2x minus G3. Okay, so you want a solution in x and y which are rational. And in general, well, it's a well-known deep theorem that there is a finite number, not a finite number, but a finitely generated group of such rational points. So that's rational points. And here I don't want to consider E over Q, but I'm considering E over the field of function on P1. So we will consider then the set, let me write it like this, of rational sections that we will write, we will call P. P is some solution x of u, y of u, right? So this is a point on the elliptic curve, so it's a solution to this equation. G2 and G3 are a rational function of u, so you want solutions that x and y are rational function of u. In general, there might or might not exist such solutions. If there exist, we have the Mordell-Weil theorem. That tells you that I'll explain the notation in a moment, but yeah, my space of function, I will write it as phi. That's the section, the rational section. And the Mordell-Weil theorem tells you that this group is a finitely generated abelian group. And so by the fundamental theorem of abelian groups, this means that there is a free part and a torsion part. There are free generators. The number of free generators is the rank of the group by definition. And then there might be some torsion elements. Let me write it Pn1. And this is the part that will play the most role in my talk. So let's call it the torsion part. Okay, so as a sub.
This is your
S, I will explain in a second. Very good. So why I put it S? Yeah, just because, and why it's called a rational section, because you can think of it in this kind of setup where it's just a rational point. So you just define a curve on a field of function, like you would define a curve on any field. More geometrically, the way we're thinking about it is that we have the base B, then there is the generic fiber, which is the elliptic curve. And so we need to pick a point everywhere, which is this point B, right? P of U. And so we have a section of the elliptic fibration. And the total space of my elliptic fibration I call S. So let me indeed write somewhere here. S is the elliptic fibration itself over B with fiber E. This is called a rational elliptic surface. They're very well understood and classified. And that's the object we discussed. So what we're looking at are the rational elliptic, I will call that the section of the elliptic curve or the Seiberg curve. By the way, terminology, when I say the Seiberg curve, I mean precisely this rational elliptic surface or the one-parameter family of curves. This is called the elliptic curve, something which is a one-parameter family of elliptic curve.
Sorry, what's phi?
Phi? This is just a definition for the Mordell-Weil group. I just call it phi. So this is the Mordell-Weil group of the elliptic curve, of the one-parameter family of elliptic curves.
Yeah, I'm not sure about the notation of ZP and
oh, sorry. ZP is also physics notation. Zn is just Z over Nz, so it's just the cyclic group of NLN.
yeah, but did you mean P1 to Zn1?
Well, yeah, sure. I mean, there is a unit decomposition if you want to. This is just a number. Then, if you want to have a unit decomposition, it would be in prime decomposition.
It should be P1 to the power N1.
Sure, if you want, yes.
Or just Zn1.
Oh, yes, I meant, well, yeah, whatever. Yeah, indeed. Later on, I will just consider some n's, and in all my examples, those will be prime number already. So let me write like this. Yes. It's just some torsion elements. Yes. So, thanks.
What's the last place we are in? Is it NH and K?
N, K.
N, K.
Yeah, just let's say that, and there might be K different torsion elements. Okay. Any questions on this? Any other questions? Sorry?
Why are you looking over the bar?
I'm working over the field of function on P on pi1, the rational function. So? Yeah, the elliptic curve is this. I mean, that's just a Weierstrass normal form of the elliptic curve. And G2 and G3 are elements of the field of function on pi1. So you want solution to this equation on this field, which is the same as finding a section of this elliptic fibration.
It's an open set on the, because it's a rational function, so it's only defined on some open set. So there are some points on D where it's not.
Well, yes, that's.
I mean, so on the poles.
Sure, I mean, yeah, it can of course, but yeah, those are rational functions.
Yeah. Just clarifying that there is no. There are some points where there is.
Yeah, they could have zeros and poles. That's not a problem. Yeah. Yeah. So and the important, well, the Mordavin theorem tells you that this is an abelian group, right? So that's obviously as written. So what is the addition? It's the standard addition on the elliptic curve. So when you map to C, it's just the addition of point on C, and otherwise it's these things that you've seen if you've ever taken some things on elliptic curves. So you have a point P and a point Q on the elliptic curve, and you look at this point and minus this point. So this is P plus Q. That is the addition of points on elliptic curve. And so for torsion points, that means that I have n times p, which means p plus p times, right, n times, equal 0, or the 0, I mean the point at infinity. So in this Weierstrass form, the neutral element for addition is the point at infinity. In particular, the crucial example in this talk will be just Z2 sections, so two sections. Z2 inside phi, so those are called two sections, two torsion sections, or whatever. No, they should not be called two sections, that's something else. Let me call them two torsions. And it looks like this, so indeed, the only way to have a point, so 2p equals 0, is to have a point like this, which is, two times the point is like taking 2 points and taking the tangent. So the point that you get is the point at infinity. And so in coordinates xy, that means that you get x0 and 0. So it's at y equals 0 in this Weierstrass form, right? In the Weierstrass form, x squared equals like this, then it's symmetric in the x-axis. This is y, sorry, and this is x. So that means that if I only consider two torsion sections, either if I have solution at all, I have either one solution, a rational point, and then the other two are related by the usual quadratic solution, or there are three rational points. Right? So if solutions exist, we either have a Z2 part of phi torsion, that means there is one solution, let me call it x0, and or you can have Z2 plus Z2, that means three solutions, which are, I will call x0 and x plus and x minus, in the following, right, that the solutions are just because, yeah, let's call this f of x, right? And so, if you have a solution at y equals 0, that just means roots of the polynomial x. So that's why you have either one solution or three solutions. So you would have f is just equal to 4 x minus x0, x minus x plus, x minus x minus. And so those three roots are either one is rational or two irrational or non-irrational. And finally, the last bits of technology I want to emphasize is the concept of isogeny. So what is an isogeny? Between elliptic curve, it's a group, well, the elliptic curves themselves are abelian groups. So an isogeny is some group homomorphism with some non-zero kernel. So we'll call that the n isogeny, and n is let's say prime integer for simplicity, and prime just for simplicity. It will be my example. My example will be n equal 2, and I will have n equal 3 if I need to at the very end, but probably not. So an n isogeny is a n to 1 homomorphism. Psi from the elliptic curve to a new elliptic curve between two elliptic curves. So remember that here I have really this one parameter family of elliptic curve. And so I want to uplift this concept of isogeny to S, the total space, and it does uplift to S. And in fact, such an isogeny is always generated by a torsion section, by P torsion, so a torsion section, and torsion section. So the picture is at every smooth fiber, we just said you can map to C to see what's going on, and the isogeny will just be some point that, for instance, this is a Z2 isogeny, so that P Z2 a two torsion. So the two torsion generated translation of the elliptic curve, a non-trivial translation. For instance, here order 2. I get back to the origin here. This is my 0. And so n torsion section generates translation on the elliptic curve, and so the isogeny is just quotienting by this translation, by the discrete automorphism of the curve. So psi will go E by E often here, I mean the full total space, the one parameter family of curve, and so in any case E prime is E divided by P. By this I mean the translation generated by P. So this is my example of Z2. So this is a two torsion, P Z2, it's a two torsion. So that means that the whole curve has this translation. The point there, it goes to the point plus there, and so on. So we can just quotient by this, and the new, so this will be E, and this is E prime. I just quotiented by this section in that direction. So that will be for a two torsion. Any question on this? Mm-hmm.
So the setup is that you're only looking at vibrations with a single section, but the single section may have a neutrino torsional part, meaning that the more elevated cube is has a neutrino torsional part, and the more neutrino, the more solutions to the right-hand side.
I could have as many torsions as I want. I'm just taking one particular. So the model group might have 3 elements, which I don't care about for the moment, and the torsion element. And anytime you have a torsion element, it does generate a translation along this torsion element on the generic fiber, and I can quotient along this translation. That's what gives me the isogeny.
I was asking more about the top right.
Yeah. Well, in the case of my example in Z2 section, I either have Z2 or Z2 times Z2. That's the only way Z2 can appear in the Mordaunt group. In the on the generic fiber, it's clear because it's just this picture. I have a torus, and the only way to have a Z2 isometry is either you are at this point, that will be called x0, let's say, or else you could be at this point, but that's the same by Sn to z. So either you have one section which is this one, or you have three sections which are this one. That's generated Z2, Z2. Those are just the only 3 points that are fixed under.
The last thing was typically if you want to check whether the conversion has another section, we cannot be in the z equals 1 patch, which is the choice, which is the implicitly negative box y2 or x squared minus g2x minus g2.
Well, we have a zero section by definition, right?
Yeah.
That's the rationalistic surface.
Yeah.
And then in this, I'm looking at a section on top of the zero section. The zero section exists by definition, by assumption.
And these are kind of the zero section.
Yeah.
Yeah, I want to be a solution to that equation.
Yeah.
But then if you really want to try to find other ones, but I'm not sure whether this is relevant for the basic for the other people. I don't know. I just don't know. You will be essentially forced to go to not sorry the z not 1 patch. Which is not contained in the.
Yeah, it might be. I mean, for the Z2 section, that's all there is. It might be like in some other case for higher torsion, there might be a solution. And indeed, implicitly, I'm working on pi1, so here it's just convenient to. I mean, on the full elliptic curve. So here I'm using xy coordinates, but there might be that there is a section that somehow intersects infinity somewhere. Yeah, it won't be relevant for today, but yeah. Okay.
Just to say, should we work on this small x cube?
Yes, of course. Thank you for pointing out this very important mistake. Of course, it's a cubic. Thank you. Yes. All right. Okay, and yeah. Oh yeah, and the last piece of things that is useful is that whenever there is an isogeny, the new, so that means I have an isogeny, that means that I added n torsion section. In the new curve, then there must exist a dual isogeny. So for instance, in my example there, the new curve will have dual isogeny, which is generated by a section which is here. And then you could quotient again, doing the same isogeny twice, and then you were left with these things, which is the same, as it's isomorphic to the curve you started with, so psi prime, e prime, to e prime prime, this is e prime prime, but up to a factor of 2. Yeah, so you could then go back to where you started, but you need to compose the so-called dual isogeny with the rescaling by a factor of 2. Okay, that was for my mathematical introduction, as promised, and now I will go to the physics description of why we care about this. Any questions on this?
Sorry, I'm being a bit slow, so I'm getting a bit confused as to whether you're taking the curve of values in the function field, or is that, so you're looking for roots of the, yeah, I mean, essentially you have the Z2 if and only if this polynomial splits, right?
Yes.
Is that splitting over the C of U, or is it?
Over C of U, yes.
Over C of U.
Yeah. So that's what I mean by having rational section. It's the solution x of u, y of u of this equation, precisely where the x and y are rational functions. Right? Yeah.
So then you're saying that as isogeny of C, or for this family, are governed by the origin and gradient.
Yes, the isogeny are governed by the sec. The thing I didn't mention is what happens to the singular fibers, but this is also well understood and we'll mention in examples. So indeed, on the generic fibers, this isogeny is like literally a translation in the C patch. I mean, in the description of the elliptic curve as C mod L. Then of course there are also singular curves where the curve become genus 0 with some singular point that you can resolve and so on. And then it's well understood also the isogeny transform the singular fibers. So we'll see some examples of that.
Are you saying that when you have Boltzmann, this will always extend to the whole family? It's not just to the bigger size?
Yeah.
Can I clarify something? So here S is the fibration over the Coulomb branch, where the electric fibers are all rational.
There are elliptic curves, yes, everywhere, and they could degenerate at some finite number of points.
Right. Okay.
Good. So, sorry?
Where does this more down base come over the function field as we go beyond it?
Well, where does it come from? You mean you want the proof? I won't be able to provide you the proof. It's very similar to the proof on Q, yes. I think it's discussed in the Silverman and Tate book or something.
What's the book name?
Silverman and Tate, I think, the discussion of the general model value group. I think they do a spectrum field as well there. Yeah, at the end. It's one of the Silverman books. I don't remember which one. Maybe there is another Silverman book a bit more advanced with that. Anyway, but yeah, you have to believe me. I mean, I want. That's the kind of thing I defer to mathematicians to prove the model. We assume that the model value group theorem is proven. It's been proven by Weil. I mean, by model and then Weil. I think Weil precisely extended model result from Q over any field.
Something tricky going on, right? Because over Q, it's just for any elliptic curve, it's Q point is fine. For here, we definitely will need the coefficient to be non-constant.
Yeah, but they're element of the field.
C point, right? So also there's something not trivial.
Yeah, I mean, yeah, that's beyond my pay grade, but yeah, the claim is that my understanding is precisely that Weil extended model's result from Q to any field. So, yeah. All right. So let me go to part 2 about Seiberg geometry. So a brief reminder of the physics for the physicists, that is, in the audience. We are starting in the UV with a 4D n equal to gauge theory. And we'll take it to be a SU2 gauge group. Although by SU2 gauge group, at the moment I just mean the SU2 gauge algebra, that will be important. So we just determine the Lagrangian in the UV. So we have a SU2 gauge theory. And so this is asymptotically free. The beta function is minus V0, which is negative, so V0 is equal to 4. A standard beta function of pure SU2 and equal to. And so in the IR, well below the strong coping scale, lambda, which goes like 2 pi I tau of mu divided by V0, then we have the Coulomb range that we care about. And so we have U1 gauge fields at generic points on the Coulomb range. Right? And Seiberg and Witten tried to solve, did solve for the low energy dynamics of this low energy photon. So semi-classically, at a large distance on the Coulomb range, this is classical X mechanism from SU2 to U1, but if you are at values of the VEV, U here that parameterize the Coulomb range, which is comparable to the lambda QCD, then you have no classical physics to guide you, so you need to be Witten to get the answer, I guess. So in physics, then U, my U parameter, which is the local coordinates on B, on the Coulomb range, was the trace of the gauge invariant things you can build from the scalar in the vector multiplet, so the Coulomb range operator, the Coulomb range K ring. That's the K ring that we said is boring because indeed this is just C. So that's what Carla was saying. Classically, this goes like A plus and those are non-perturbative correction, and they're important. So classically, you would just go on to Coulomb branch, which is just diagonalizing the scalar. Then U is A squared by the X mechanism, but then you and A would be the fluctuation of the low energy photons. But then the relation between U and the low energy photon doesn't need to as quantum corrections, of course. And an important player in Seiberg-Witten theory is that there is also electromagnetic duality, in IR that exchanges precisely A. So A I will call the photon by Abusov notation. That means the scalar in the same multiplet as the low energy photon. It exchanges a photon to a dual photon, right? Just by the Maxwell duality. Maxwell, who invented electromagnetic duality? Some guy in 19th century. Anyway, the Maxwell equations are invariant under exchanging electromagnetic fields. This extends to supersymmetry here. No, it first appeared in some paper in the late 19th century by the same guy who did, what's his name?
I mean, the modern formulation in terms of
yeah, but the Maxwell equation, people notice already a bit after Maxwell that the Maxwell equations are invariant if you set the source to 0. And yeah, anyway. Some British guy, I cannot remember. Heaviside, thank you. So it's really the Maxwell Heaviside duality. Yeah, electromagnetic duality. Thank you. So yeah, so here just a reminder, right? I'm not gonna derive all of the kinematics, but A and A dual are related to each other, and most importantly, they are related to the prepotential, which determines the full Lagrangian prepotential F. So the data of the prepotential is the same as knowing A and A dual, the low energy photon, and it is dual. They're related like this. A dual is dFdA, and then physically what we care about is the low energy gauge coupling on the Coulomb branch, which is the second derivative of the prepotential. So it's E dA dual dA. And then the Seiberg-Witten ID is that you identify an elliptic curve, so there exists an elliptic curve, the Seiberg-Witten curve, such that, well, my tau here, which is just a gauge coupling in physics, becomes the modular parameter of this elliptic curve. And so it depends on U, the Coulomb branch parameter. Such that tau of physics is indeed tau of U, the modular parameter. So to have that, you will identify those A and A dual as periods of the curve. More precisely, the derivative of dA with respect to U is what I called omega A earlier, and dA, du, dA dual, dA is what I call omega D. And so the derivative of the physical periods are the geometric periods of the curve. And so in particular, this is the same as omega D, omega A default. So yeah, so it geometrizes the question of, it geometrizes in particular electromagnetic duality, because now this is just the electromagnetic duality with some SL2Z action on the low energy photons and so on, but then now it becomes just the geometry, just the large diffeomorphism of the torus in the elliptic vibration. Right? So the SL2Z that transform tau by linear, by fractional linear transformation. So for the SU2 theory, then, well, what we need is to find the curve. So that's written down in the second Seiberg paper. That will be called the SU2 curve. It's written here in terms of G2 and G3. Those are the particular polynomial in U that gives the curve. Lambda is my lambda QCD, my strong Commit scale. You could set it to 1, but it gives a dimension of mass for your theory. So G2 and G3 are there. In particular, you can compute the discriminant of the curve, and the discriminant is lambda A U squared minus lambda 4. So the curve looks like this. I mean, the Coulomb branch looks like this. This is B. There is a singularity at infinity, at U equal infinity. And there are two singularities here at U equal plus and minus lambda 2, which are those two singularities there. Right? At those points, you have double point singularities. So in there, I will have to just use some notation, and that will be for the expert. They know what it is, and otherwise, those are called I1 singularities. Those are double point singularities, and at infinity there is a I star for singularity. So all of the singularity structure, the way Seiberg came about it is precisely to argue physically why we should have these singularities. So the singularity at infinity is easy. That is semi-classical physics. Is determined essentially. The 4 there is the same B0 I said is a beta function of SQCD. So that's determined by low energy, by semi-classics. While here it's a non-perturbative guess or what should happen. So the physics of those singularities is that some of the photons now are low energy coupled to massless particles. So at the singularities, often called the Seiberg singularities, well, there are the following dions that become massless. So gamma mu is 1, 0. So I should set my notation for gamma. So in my low energy theory, I just have a photon at very low energy, but in general, I can also have massive particles. Massive particles are which are at BPS, and so all you care about, I mean, all you need to know is their charges. This is the magnetic charge and the electric charge under the low energy photon. Yeah?
What is I1 and I4?
I1 and I4? Yeah, those are so there is those are singularities of the elliptic vibration. So it's all the curve that generates. So in the I4, in XY coordinates, this is a smooth elliptic curve, and the I1 singularities is when it pinched like this, with a double point singularity. And I4 star is a bit more complicated, but there is a known classification of the generation. So this is the Kodara notation for the Kodara singular fibers. Yeah.
And you don't care now about normalization of a magnetic structure. So you write 1, not 2.
Yes, I will care about it. Yeah, I will discuss a bit that. But yeah, this is we are in the SU2 theory, so this is natural normalization precisely for the monopole. That's the minimal monopole in SU2.
But yeah, I would have used 2.
No, it's for SU2. This is the only monopole because the other one would have.
It corresponds to the charge.
This is the monopole. So the dian is minus 1, 2. So those are the two particles that vanish. The magnetic. This is the.
It's not a fundamental formation.
Yes, that's true, but that's it's the magnetic. That's the magnetic lattice. That's the generator of the magnetic lattice of SU2. Not of the algebra.
And for SO3, you will write 1/2 of
in SO3 in the SO3 monopole, I mean the minimal monopole in SO3 would be 1/2 in a normalization, but then of course we will change the normalization for SO3. Yes. Yeah. So an interesting to know is that in general, as I mentioned, they could be BPS particles at any smooth point on the Coulomb range. They are massive, so they will be the so-called BPL spectrum. And you want to know which of the charges M and Q are populated in the So the BBS spectrum can change as you change the parameters u, but there will always be bound state of those two in this case. So it's often encoded, I guess, in this audience I should have specified one quiver. So this is the so-called BPS quiver, where the number of arrows is given by the Dirac pairing between gamma, so gamma m, gamma d is equal to 2. That is the Dirac pairing between those two diagonals. And representation theory of this quiver governs the spectrum of BPS states. Now, an important point here is that the spectrum, whatever it is, will depend on stability parameters, but it's always bound state of those. So the spectrum will always have even integer, even electric charge here. So spectrum will be always of the form integer times 2 integers. Right? So that's a subset of this. And BPS spectrum. And so that means that it preserves, at low energy, it preserves a Z2 one-form symmetry. Let me elaborate a bit more on this. So, given the elliptic curve, we have a lattice gamma, which you can identify with the homology lattice. And in particular, so an element gamma in the homology lattice would be like what I call the M gamma B, I guess, plus Q gamma A. So this lattice will just have two generators, Z2. And the Dirac pairing gamma prime here is the same as the intersection pairing in homology. I just have A and B cycles or whatever, and I just have an intersection between them. So gamma is identified as the SU2 charges, electromagnetic charges. So those are all the representations allowed in the SU2 theory in the UV. The SU2 representation in particular would allow for 1 instead of 2 there. That would just be the fundamental of SU2, but it doesn't appear in the spectrum. That's just a non-trivial dynamical fact about this theory, that it doesn't appear in the spectrum.
Yeah, that was my point. The same is true for the magnetic charges, because really the fundamental the operator would be 1/2 in your unit.
No, in an SU2 theory there is no such Toft operator because it will have non-trivial Seiberg class. It's not an SU2 representation. It's not an SU2 bundle. It's an SO3 bundle. Yeah. So then we can look at gamma at SU2, which is a subset of SU2 of index 2, which are the allowed charges, meaning the one that can be dynamically realized at any given point on the Coulomb range, in principle, according to this constriction here. And so gamma mod gamma at, which is Z2, is isomorphic to what I call the one-form symmetry. This is correspond in fact to the lines that are allowed in the theory that cannot be screened. So in this element, those are the line of charge gamma line equal, well, they're all generated by the element precisely 0, 1. Okay? So precisely this is the fundamental Wilson line in the SU2 theory, and because there is no dynamical particles that can screen the fundamental Wilson line, this it has a one-form symmetry acting on it. Right? Good. So any questions? questions on this? Let me write also a little the same story here with a lattice, maybe that's useful. So this is magnetic and electric charge, Q. So you have a Z2 lattice. And the allowed charges there are just the one with even electric charge, so those points, not this one. And so on. So on the other end, gamma 0, 1 here, that will be gamma L. This is the line that cannot be split. Okay. All right, so now comes for the how we can see this. I mean, all of this we knew already physically. Now the question is, how do I see that geometrically in the Seiberg geometry, and given that, I can understand better the structure of lines, which is our motivation here. We really wanted to understand the structure of lines in the, well, in any rank 1 theories directly from the Seiberg geometry. Any questions? So here is my general claim that for any rank 1 theory, but here let's say just for a Z2, the Z2 case, it generalizes. So Z21 is precisely encoded in the modal value phi of S. Of torsion sections, so the torsion part of this. So the torsion section, up to some idea that won't be relevant here, the torsion section encodes the one-form symmetry. So the general claim, in general, you will identify the torsion part of S. In general, you might need to mass deform if there are mass parameters. For pure residue, there is no mass deformation. In any case, that's the generic curve. It will have a modal group. Well, if it has one, then you identify with the one-form symmetry, gamma 1, if the Seiberg curve is principally polarized. So in my case, the principal polarization condition is just the condition that I can identify the direct pairing there with the homology lattice without any rescaling between the two concepts. In fact, there is an interesting connection to what Matthew was saying yesterday, because a better way to understand these torsion sections is as generating a discrete gauge theory, a Z2 gauge theory, for instance, in my case here, which is precisely what you would expect when you have a spontaneously broken higher form symmetry, which is what happens always on the Coulomb branch. The electric Z2 is spontaneously broken, and then you see the effect from this discrete gauge fields. So, this is the SU2 curve.
When you write the frame that way, clearly if you have one-form symmetry, which will show up in the model group. Are you saying that equals? What is the claim? That one is
the general claim is this, that the model group, the one-form symmetry is the torsion part of the model group for the maximally form curve. Like in cases, for instance, n equal to star, there is also a mass deformation. So you want to have the maximal deformation.
So this is just a discrete one form symmetry that captures like
yes.
The model group, right? Is there any such notion for more generic one form?
I mean, all of the case of interest here will be discrete, right? What happens, I mean, on the Coulomb branch, at very low energy, when you don't have below the mass of any BPS states, then there is it's Navier theory, which then has a discrete one magnetic, one electric, one form symmetry, but it is always broken to a discrete group precisely by the BPS spectrum.
Yeah, okay. So what about the non-principally polarized?
will get to it right now. So next slide. Let's gauge, right? If I have a one-form symmetry, I can gauge it. Well, I can gauge it if it is non-anomalous, but this one in 4D is non-anomalous. So we can gauge Z2, 1. It will be a so-called electric one-form symmetry in this case. So again, we can make a general claim about Zn1 gauging. So you start with an elliptic curve with a P n section, n torsion section. So which is part of the torsion part of the Mandela group. So that will represent my correspond to my n-form symmetry. And then I can do my n isogeny psi, and I will also rescale by a factor of n, square root of n. So that will be called E prime equal E rel. That's a new curve that you get following the isogeny. And then, in general, we will need to do a second step where you do the same thing again. I prime, and you get E prime prime. So let me explain. So in this case, we had the Zn, which was part of phi torsion. For simplicity, let me say it's equal to, but it's only this, for instance. So okay, we have a Zn torsion section, and we do the isogeny along this section up to this rescaling there. In this new curve here, the Mandela group, precisely in the case where this holds physically, you get Zn plus Zn. So there will be many more torsion sections, or the Zn subgroup of Zn plus Zn. You pick one, you pick P prime, right? And so this is along P prime, this is along P here, P0, let's say. Okay, so we pick P prime, and then you do an isogeny around that. If P prime was actually what I call the dual isogeny, then you will get back exactly where you started. And you saw that in my example with n equal 2, when you do twice the isogeny, you just get the same curve up to a factor of 2. But this is taken care of by this rescaling by square root of 2, square root of 2 back. So we're back where we started exactly. But if you pick a different subgroup, I mean a different section, because you have Zn plus Zn, then you will get a different curve here. And that's, in fact, all the possible gauging of this. It ends on this curve here. And this curve will then also have just a Zn one-form symmetry, which will be like the magnetic dual when you gauge. The square root of n rescaling is quite important and justified physically. Let me just say in words, because you precisely want to preserve the direct pairing. So when you do these isogenies, the period will transform in a certain way that would just break the connection between homology lattice and direct pairing. So you need to put this square root of n factor precisely so that the spectrum of BPS state doesn't change. So that's a physical requirement to preserve the direct pairing. But then what it does imply is that this curve in the middle, if you start with a principally polarized curve, this one is not principally polarized. So this is what I will call the relative curve. And it's not principally polarized. In that case, the interpretation, so those are the one-form symmetries, while here, in fact, this is what is known as the defect group. So those are all the possible lines that would be allowed by the algebra, but they are not mutually non-local. They are mutually non-local in general.
Associated to the Gothic institute.
Exactly. So if I don't, so you can follow these isogenies. In fact, you can do it at the level of this my Weierstrass equation, y squared equal 4x cubed minus g2x minus g3. there is an explicit formula that maps one G2, G3 to the one along the isogenies for the n isogenies. It's known as the Velu's formula, so you can just apply it. It takes 1 second in mathematics. And so if you go from SU2, you go to this one, which is the other one. That is the relative curve. By the way, historically, this one appeared in the second Seiberg paper, this one appeared in the first Seiberg paper. But with a slightly different normalization because of this factor of square root of 2 or square root of n that I mentioned. But so here, the interpretation of that curve is actually that it's just a relative curve. So it doesn't know about the lines, or it knows about all the lines in a sense. And so when you start from the SU2, you can do an isogeny in that direction, or in that direction, you get the SU2 or the SO3 form of the group. Famously, there are two forms of SO3 group, SO3 plus and minus. Those are the plus and minus here, and this is my curve. As far as I know, this curve has never been written down before, but the correct picture was given in some lecture by Yuji in 2013, but no one bothered to write this curve. To actually find this curve, right, I mean, I didn't guess the factor of 216 and so on, it's just following the isogeny. So it gives you the curve with all the right properties. And in fact, let me discuss some of those properties physically. How much time do we have left?
That was 10 minutes.
Okay. So here, let me write all the curves indeed. So the SU, the curve, I mean by the curve, I mean the Coulomb range. We'll discuss the physics, right? So here we said we had I star 4. You do a 2 isogeny, you get the relative curve, which has a I star 2, I2, I2, and another 2 isogeny. Those are the SO3 plus and minus curve. Let me write two of them. SO3 plus, SO3 minus. So the fiber at infinity is I star 1, I star 1, and then I have an I1 and an I4, and an I4 and an I1.
In terms of these two isogenies, how do I select SO3 plus versus SO3 minus?
In terms of the relative curve, you have these things, it looks like this. So in my omega dual omega frame, let's say. So P0 is the one that gives you back SU2. And then the two other tertian are this generator or this generator. So this one is the one that gives SO3 plus, and this one, essentially, this is the T transformation that you need between the two. Right. So yeah, it's interesting to look at the BPS state for a second. So those we said was like 1, 0, minus 1, 2. So they're all conjugate to 1, 0, right, in SL2Z. So that corresponds to a single electron becoming massless, a monopole, which is an electron in S dual frame. In this case, because of this square root of 2 factor, you need to put square root of 2 here, and how do you write this? Will be square root of 2, 1, 0, and square root of 2, minus 1, 1. So those are the two BPS states. The fact that it's square root of 2 is because it's an I2 singularity. An IN singularity at low energy physics means that the beta function is equal to n for IN. So here that means that you need an electron of charge square root of 2 that gives n 2 because the beta function is q squared. And finally, you have those ones. And so in that case, for SU, the charges of the dions and the monopole, let me get it right. So the monopole for the SO3 plus would be 2, 0, and gamma D is minus 2, 1, while in this case you would have gamma D is equal to minus 2, 2, and gamma M, the monopole, to be 2, minus 1. Okay, so you see that the monopole in DSO3 plus, to answer Stefano's question earlier, now it's 2, 0, that is the monopole, the actual monopole, physical monopole, closed polar plus monopole at adjacence on U plane. But that's the one that you would SU2, while in the 1, 0 would be the minimal bundle on the sphere for SO3.
And I think for the relative curve here, the curve for UN, when I factor out the center of C1.
UN?
UN, or
U2, yeah.
When I factor out the
I'm not sure, maybe, yeah, let's think about it. I haven't thought about it that way, but...
It's a dual of UN is still UN.
Yeah, then forgetting about the U1 which is decoupled. Yeah, maybe something like that. Might well be. Yeah, I don't know about but the important part is the square root of 2 here to precisely preserve the direct pairing. So Seiberg and Witten would have written those things without a factor of 2. Then this is the stand, in particular, the W boson is 0, 1. But then in that normalization, you don't get the same, you don't preserve the central charge as you go between the different curves. Right, so finally, so the important point is to check that the physics of the SO3 curve is what we expect. As I said, this is a new curve as far as I know. So the first thing you notice is that you've broken the symmetry between the two I1 singularities. So the symmetries between the two I1 singularities in SU2 comes from a spontaneously broken R symmetry. There is a Z8 R symmetry in the SU2 theory in the UV, which is spontaneously broken. And there is a part of Z2 of it which acts on the Coulomb branch parameter, sending U to minus U. Yeah? So that's a spontaneously broken R symmetry, and so the two vacua are the same. In fact, famous in the Seiberg paper, you can deform this theory to n equal 1, then those gives two confining vacua for the n equal 1, which are equivalent, because they are related also by the R symmetry of 4D n equal 1, SU2 theory. In this case, the two Seiberg singularities are not equivalent. Then when you deform to n equal 1, you have non-equivalent vacua, that is indeed well known. The reason is that in the SO3 normalization, if you start with SO3, you don't have an R symmetry. One way to phrase it is that there is in fact a mixed anomaly between the R symmetry here and the one-form symmetry, and when you gauge this one-form symmetry, you break you don't have the R symmetry left here. So those are two distinct vacua. They have different, so this one will still confine, but this one doesn't. The basic reason is that now you have an electron of charge 2, so there is a leftover Z2 discrete gauge field in the infra. So you have a different vacuum structure. And on the other end, when you change, so there is no R symmetry, but you can still do the same. That will be equivalent to doing an R symmetric transformation, which is the same as shifting the theta angle by 2 pi. In that case, it will just be a symmetry of the theory. Theta goes to 2 pi is a symmetry. But in the SO3 theory, theta is valued between 0 and 4 pi. And in this case, this is shifting theta by theta plus 2 pi, and you go from one theory to the next. And in that case, theta goes to 2 pi, you just shift lambda squared to minus lambda squared, which explains the plus and minus here. So it goes between one curve and the other. And it exchanges the two singularities. So,
the last time there is lambda squared.
Plus and minus lambda squared, thank you, yes. Yes?
Is the differential always the same for this
yes, no. Well, the differential is, so dx, dy, and then the Seiberg differential is related by some factor of 2 or 1 over 2. Yes. It's accounted for. But yeah, it's easy to keep track. But it just gives a rescaling following the isogeny. So that's about n equal 4, and if I had more time, which I don't, I would have discussed next generalization to less well-known theory, which are 5D SCFTs. Now you can do the same game when you have 5D theory in a circle. You would have, similarly, there are 5D theories with one form symmetry. When you reduce to 4D, you get a one form symmetry plus a zero form symmetry. So there are more things you can do. You can gauge the one form, the zero form, or both at the same time. There could also be anomalies in 4D one form symmetry in 5D, which comes as a mixed anomaly between zero form and one form. So in those cases, you will see that it also appears when you try to gauge using this procedure. So there is a nice picture about 5D, which is similar to this, but with more bells and whistles because there are most mass deformations and so on and so forth. But the take-home message is that one-form symmetries are encoded in the Mordell-Weil group of some principally polarized curve for any rank 1 Seiberg geometry, and the gauging is just done following isometries, where in the middle you find relative curves. So given the relative curve, you can get all the absolute curves. A very interesting point would be to generalize to higher rank, but the old technology of elliptic curve is not there, but there should be some similar picture, because in fact, in most cases of, for instance, SU and Yang-Mills, the only Seiberg geometries that are known are relative, what I would call relative curves. People seem to be fine with it, but I think there will be slightly different construction of the curve that will give all the absolute curve that encodes the line, because in the literature so far, people just put the line kind of by hand. So that's it for me today. Thank you.
Thank you very much.
Are there any questions? So, in the context of class S theories, what is this isometry do to the base curve, the base curve of your algorithm curve?
I haven't thought about the class S picture much, so that's a good question, but I'm not sure I want to venture an answer. But yeah, that would be. Yeah, I'm doing something very elementary, just using Weierstrass model of the Seiberg curve. Of course, there are zillions of other geometric and class S engineering construction. There's been a lot of discussion of wire form symmetry in this context. There are ways in which it should match, but it's not always obvious.
So now to take the total space of this vibration and you excise some locus, so you should get the symplectic singularity. Well, or maybe in your case, might not be a singularity.
So at least
singularity was at the 3D
yes.
branch of the 3D series. Did you look into that?
No, not yet. Yeah, that was my outlook part. Yeah, I didn't do part 3.
S2 you get teaching, whereas S3 you get a double cover.
Yeah, so it will be indeed in the teaching system some sort of double cover of one to the other, which I don't think have been looked at in much detail, but I haven't looked at even the literature at this point. So I think that's completely work.
The result is not, I guess. How to go from
to go between different ones to see what I would call the relative curve and so on in this context. Yeah, there should be, and of course, there will be a way to generalize to any rank and so on, because if you each system for AN, whatever, there should be a way to see all the different global forms by just slightly tweaking or using by etching system. Indeed. Yeah, and that would connect to 3D and equal for physics.
So, is SO very plus minus? It's kind of related to SU2 with the message. I think very flavors.
Oh yeah, that's a good point. Well, it is indeed the same curve up to some normalization. What matters is that this one is indeed the same Seiberg, the same one parameter family of elliptic curve as SU2 with 3 flavors, SQCD. But the key difference in that case, the I4 singularity here can be broken up. So you can turn on masses, and then I4 become 4 I1 singularities with generic masses for the, in that case, there is an SU4 flavor symmetry. SU4, which is SO6. Yeah. But here in this picture, those are so-called undeformable singularities, because the low energy physics is that you have one particle of charge 2. So there is no mass term. While in SQCD case, at low energy the low energy physics is you have 4 particles which are mutually local, which become mass at the same time. And so you can then give mass to them and deform. So it's the difference between undeformable and deformable singularities. So it's an extra data in a sense that we impose physically. Compared to.
I have 2 questions actually. One is you said that you go from SO plus to minus at the level of the curve, you impact the sign of lambda. Is it easy to see that you S to connect SO2 with SO at the level of the curve?
Sorry, second.
Is it possible to see in an easy way how the action of the S of SO2Z will connect the curve of SO2 with the one of SO3?
Well, it doesn't because there is no S duality. It's pure Amiens. But thank you. That maybe I can take a minute to explain a different section of the paper. There is a S-duality if you add an adjoint. Right here there is no S-duality, so SU and SO are different theories. They are not related by anything. But if you look at 4D n equal to star, so that SU2 is a massive adjoint, then there are two curves in that case. One is the relative curve again, which looks like 3I2 singularities. Right? So two of the I2s are the same as my relative curve, and the extra I2 is the adjoint in some duality frame. And this is a SL2Z invariant, so that just permutes the 3I2. But this is the relative curve, but if you do the isogeny, you find the absolute curve. And the absolute curves look like I4, I1, I1. And there, this is gamma 02 invariant, if I'm not mistaken, and this is the actual S-duality group. And it does relate the two. So in particular, now you can send the mass of the adjoint to 0, but in different S-duality frame. So in the SU2 S-duality frame, you will send the mass of adjoint to 0. This goes to infinity, and you're left with pure SU2. In the other S-duality frame of SO3, you will send this one to infinity, and then you're left with this curve of SO3.
I'm a bit confused because I have in mind the reading between the Amiens paper, and in that case, the SU2 and the SU2 plus, I think, are connected by this.
Yeah, but this is, I mean, it's not a duality of the theory. It's an operator.
Yeah, it's connecting two different
yeah.
So two different theories, but they're connected by X.
This is the isogeny two-step.
In a sense, that's what the isogeny does, but that's a gauging of a one-form symmetry. The way it's written, it's connected by S. I think it's only if you have S duality, then that is the actual symmetry of the quantum theory, right? Then it does relate n equal 4 with SU2 with n equal 4 with SO3. And this is seen in this curve, or in this curve, very nicely.
The other question I had is if for the higher rank generalization, the challenge is that there is no analog of the bias transform, some canonical way.
Yeah, nothing generalized on what I said in higher rank. So I love rank 1 because I like elliptic curves, but you can have higher genus Riemann surface or whatever you want to describe it. It's not, you don't have an abelian group structure, you have nothing. So yeah, there is no analog of torsion section or anything like that. So there is still some geometric engineering, so one can try. Part of those things really secretly embeds, and a lot of motivation for this comes from thinking about in type 2B, embedding this in a kind of Orivapa type picture, but
what's the family RP for this SO3?
Oh, good. Yeah. I have the curve somewhere, but we can discuss in private. But yeah, I mean, there is indeed it's interesting because in 5D there is SU2, and then you can gauge the one-form symmetry of SU2 of the electric SU2. That one-form symmetry in 5D does not have an anomaly either, so you can gauge it. But then you get SO3, which has a two-form symmetry. Then you can put on a circle my KK theory, but then this theory will have a two-form and a one-form symmetry. And yeah, the curve looks a bit more funky, but we understand it. And it has a limit to this curve, of course, in some way.
Maybe we can postpone the discussion for later because we are out of time. Let's thank Cyril again.